Hi everyone. This is the first part of a 4-session course on the Introduction to Statistics. For week 1, we'll cover distributions, specifically central tendency and variability. In this slide, we'll look at our course overview. For our goals, our primary focus is on concepts. By learning these concepts in statistics, they carry on to further concepts, and these are the foundational concepts that will help you in any type of analysis. Our second goal is to allow you to use multiple methods when examining data in your work. Hopefully, from this experience, you'll gain multiple approaches at examining data. And for our third goal, it's so that you'll interpret results and assess the quality of an analysis. For the content, I will provide text, notes, video, lectures, data, and a graphic user interface. You have different options of analyzing data, so whatever your preference is the way to go. That's either SAS, Stata, SPSS, or even Excel. But if you'd like to replicate the analyses we do here, you can do that through the GUI that I've provided. The Stats with Steve team site will have files and is a place to ask questions about the course. And for our data examples, we use the U.S. Department of Health's COVID-19, the Titanic, and motor trend car data sets. Within the area of statistical learning, I'll be following the themes discussed in the book, How to Think About Statistics. The author stresses an importance in understanding concepts as well, and it's kind of what I'm basing this course on. I found this is probably one of the most useful books I've ever read on statistics. The author also points out that subsequent concepts are built off of prior concepts. So if you learn one concept, it helps to learn the next. So if we learn the most important concepts early, in the fourth point, we expect that understanding these concepts can help identify opportunities for investigation and to show the most useful results. So one of the most powerful tools that you'll have is the ability to identify when you can apply statistics and when you can show important results. So if we can help you to better understand these concepts, ideally it'll open up new opportunities for the work you're doing. And maybe the first question we should answer is, what is statistics? And this is from the Moore McCabe book handout that I have provided. And they answer the question, what is statistics, by stating that statistics is a science of collecting, organizing, and interpreting numerical facts, which we call data. So we often plan studies where we collect data. We organize that data. Usually it's when we construct our data sets, and we interpret the results from our statistical analyses. Another question we might ask is, what do we do in a statistical analysis? There's generally two parts to it. The first part is to describe the sample or population. We examine the center, spread, and shape of a distribution. In statistics, we really think about distributions. We often report single number summaries such as the mean or the standard deviation, but when we're thinking about the actual results and what we're trying to interpret, we're usually thinking about a distribution rather than just a single number. And that leads us to the second thing that we do in a statistical analysis, and that is to make inferences from the sample onto the population. In other words, my sample is part of a larger population. And some of the questions we might ask are, is one group sample part of the same population? Or does a group's center and spread differ from the population? So in other words, we do two things. We do descriptive and inferential statistics. And the stuff the statistician does varies. It ranges from planning a study, producing graphs, and performing statistical tests, and includes interpreting results. And another fundamental part of what a statistician does is tells a story with data. And this is something all of you already do. But we have some options that that we can cover that may supplement the work you're already doing. So for telling a story with data, there are many parts. Each graph or statistical test can make up a chapter in that story. In other words, we rely on multiple analyses. Now we'll begin with distributions. We'll discuss the center, the spread, and shape of distributions, and how we can use that to understand our data better. So we often receive data in different ways, and this data could be in different forms. And accordingly, we have different levels of measurement. For example, for a nominal level of data, these are named levels, such as a medical center name or a medical record number. In other words, these numbers or categories just represent a name. Our next level of measurement is ordinal. These are rank-ordered. Distances between levels are not assumed equal or meaningful. For example, first, second, and third places in a baking contest. The value of 1 between each level doesn't have any numeric meaning to it. Our next level of measurement is the interval level. This data is rank ordered and has meaningful distances between levels, but has no zero. So, for example, SAT scores, they range from about 200 to 800, or they used to range in that. And for our final level of measurement, it's the ratio level. This has all the qualities of the other levels of measurement, but it includes a zero. And an example of that would be ounces, weight, or money. Could be a savings account, and it is possible to have a value of 0 there. And what's one of the important things to consider is how this can determine which statistical test you will use. For example, if I'm looking at the age of patients on the Titanic, we'd probably use a ratio level such as a t-test. If I was looking at whether they survived or not, that's more of a nominal or ordinal level. Survival could be coded yes, no, and for that we'd do a proportion test. And we often use a normal distribution to develop tests or other statistical properties that we can use for it. In the next few weeks, we'll cover something called the central limit theorem, and that tells you if you have repeated samples, they will eventually form a sampling distribution. So although you might have skew data, a collection of summary statistics would most likely form a normal distribution, and the bigger the sample, the more normal that distribution looks like. So it's an important part of statistics, and we can see it on the top left as a normal curve, and another way we might describe that is a density plot or density curve. And on the top right, we have what's called a histogram. This is similar to a bar chart, but you'll notice that the bars or the bins touch. And on the bottom, it's an example of how we form a histogram. Each bin contains the count of cases with that range of value. For example, 40 people had scores between 35 and 40. And so as we fill the bin, as we get the frequency on the bins, that forms a histogram, and we can get an idea about the shape of the distribution that way. And now we'll cover the center. And three statistics that can give us information about the center are the mean, median, and mode. And in this graph, we see the measure of central tendency is in a positively skewed distribution. And we call it a positively skewed distribution because we have our tail trailing off to the right. If this tail, this long edge, if that was pointing to the left, we'd call it a negatively skewed distribution. But in a positively skewed distribution, we can see how the three values differ. The mode represents the most common value, and in a distribution that would be the highest point of that distribution. The median represents that middle value, and then the mean would be to our far right. In a skewed distribution, the mean gets pulled in the direction of that skew. So if we were looking at a negatively skewed distribution, we'd see the mean over to the left, the mode to the right, and in the middle we would have the median. So we have the arithmetic average, and that's what we call the mean. But in statistics, we have a general term for the average, and that's just the most common description of that data. And there's three different ways of saying what that average is. It could be either the mode, which is the most frequent value, the median, which is that middle value, which is helpful for skewed distributions, or it could be the mean. So we have different ways of saying what the average is, but the idea is to give us an idea about the center so that we can describe that distribution and eventually gain inferences from it. So for this, we'll use some sample data from the mtcars dataset. mtcars stands for Motor Trend Cars. It's an old dataset that we can use to look at different car makes, and in this example we'll look at miles per gallon. So another useful value of variability is our percentiles. They are the percent of the distribution at which a certain percentile falls below that value. For example, 19.2 is the 50th percentile, or the median, in miles per gallon. 50% of cars in the sample have MPGs at or below 19.2. And you can calculate percentiles from 0 to 99, and a useful sample size to have is probably at least 40, so that you can have your percentiles differ by 2.5, and that would allow you to have the middle 95% with a sample size of 40. Another measure of variability is the interquartile range. This is the distance between the 25th to the 75th percentiles. For example, with miles per gallon, the IQR is calculated as 22, which would be the third quartile, or the 75th percentile, minus the first quartile, or the 25th percentile. That value is 15.4. So 22 minus 15.4 is equals 7.4 for miles per gallon. So that it's an important value to remember, because it gives you an idea of what the spread is. If you are working with a skewed distribution, the standard deviation has issues where the interpretations you get from that become less and less accurate as your data gets more and more skewed. But a very good measure of variability with skewed data would be the interquartile range. We also have the full range, and that would be the lowest and highest values. For miles per gallon, our lowest MPG was 10.4 and our highest was 33.9. So from this information we can calculate what's called the 5-number summary. This is the range and quartiles, the 25th, 50th, and 75th percentiles. For MPG, it is our 5-number summary is 10.4, 15.4, 19.2, 22, and 33.9. And another measure of variability is the standard deviation. This is one of the most common ones we use. It gives us a lot of information and allows us to look at our data in different ways. The standard deviation is the average square deviation around the mean. So it gives us an idea what kind of variability is around our mean or our center. So in this slide, we're looking at the proportion of data within 1 and 2 standard deviations of the mean. We have something called the 68, 95, and 99.7 rule for 1, 2, and 3 standard deviations around the mean. So the values you see here, 0.14, 0.34, 0.34, 0.14, and values of 0.02 at both far ends indicate the proportion of area that's within each standard deviation. So we call it the 68, 95, 99.7 rule because within 1 standard deviation of the center, and our center is at 0, we would see 68% of the sample within that 1 standard deviation of 0. Within that second standard deviation, we include another 28%. So that would give us about 95%. And then in that third standard deviation, we would end up with about 99.7% of our sample scores likely falling within 3 standard deviations. And I think those end in these little dashes right there at not quite at the end of the distribution. It's important to note for the normal curve, these tails go out to infinity, so it would allow for even the most extreme values. It would just assign a very low probability. And you'll notice that as the proportion gets bigger around the center, we're looking at the area under this curve. So there's more area under the curve around 0, and that's why we see 68% of the area being around 0. And so we have, as an example of how the mean, how we can have 2 distributions with the same mean but different variability. This graph shows us the data with the same mean but different variability and how different these 2 distributions can look. So if we're just looking at one single value, which is the center, the mean, we can miss out on important information about distributions, and this will be especially helpful as we look at differences between groups. And so in this example, we're going to look at density. So what you're looking at is something that comes up from my Shiny app, and we're looking at COVID data. And we're looking at how things changed over time, going back to January 2020. So in January 2020, beds were not overutilized in the U.S. as COVID spread in the next 1.5 years, bed use increased consistently across the country. So you'll notice that there are letters underneath this red curve, and each of those represent different states. So for California, we have CA that represents our state here in Southern California. And you can see how different states become more consistent on their bed utilization. On the x-axis, that ranges from 0 to 1.0. These are proportions, so we can see that back in January 2020, the inpatient bed utilization was across the nation was about 46%, and then about a year and a half later, it's about 74%. So these are density plots, and the purpose of this is that it allows you to show changes in that distribution over time. We can see that we would find these changes over time significant and substantial. But these are just different ways of showing a distribution and how we can gain insight from looking at these different distributions. And we can see that over time, inpatient bed utilization shot up in the U.S., and we would consider a big contributing factor that would be COVID. So for this, we're going to also look at inpatient bed utilization, and we're going to look at the summary of variables from our COVID data. And this gives us information on center and spread. So on the first column, we have the average for inpatient bed utilization. We have our 5-number summary. It's common to report these. You may only use one or two of these values in our daily work, but this gives you an idea about the range, and we also have something about the center and the median and the mean. And we have different variables with the same values. We have the standard deviation that gives us an idea about the spread. And we also have something that's not commonly used, but it's called the coefficient of variation, and it's the standard deviation divided by the mean. And so that gives us an idea of how much variation we have. For normally distributed data, the mean is usually bigger than the standard deviation. A bigger standard deviation would suggest that we have a lot of variability in there. And that would signal that although for the mean, those values are consistent, can be consistent even in skewed distributions. Because of that, we gain more use out of the mean and skewed distributions. But when we talk about variability, specifically standard deviations, as it becomes more and more skewed, that becomes less and less reliable. And there are special considerations that we should note. The first is that non-normal distributions are common. We can still use the mean to estimate important values. For example, length of stay values are often very skewed but stable over time. The mean might be 11 days, and that value would be helpful for projecting staff requirements and so on. But to describe the average patient stay, using the median of 2 days is more appropriate. Also, another consideration is that with skewed distributions, be careful about your interpretations that use standard deviations such as control charts. For example, applying the 68, 95, and 99.7 rule fits on the inpatient bed utilization outcome because 0.14% falls above the third standard deviation. in a control chart, but it overestimates the inpatient bed utilization for COVID patients. 2.17% fall above the third standard deviation of the expected value. So if you're using control charts, it could overestimate that. In some cases, it can cause an alert when you weren't, where it's not appropriate. So in this graph, or in this slide, we have examples of other distributions. On the top right, we have negatively skewed distributions. And on the bottom left, we have a positively skewed distribution. And you can see for negative distributions, negative skew, we see the tail drifting off to the left. For positive skewed distributions, we see the tail drifting off to the right. And in the bottom right, we have an interesting case of a bimodal distribution. And this is something that we can come across in various sets of data where under one somewhat normal looking distribution, we actually have two underlying samples or two underlying distributions. In this example, it's men and women. And we have a somewhat normal looking distribution, but we start to see what could be two different populations within this bigger set of values. Men and women may differ. We'll want to examine this more. And so that brings us to the section on analyzing data. We'll use descriptive and inferential statistics to explore data. And for this example, we're going to look at the Titanic passenger age. We have a histogram on the average age of our passengers. And we have two vertical lines. We have a purple line that represents a dashed purple line that represents the median of 28. And we have an orange vertical line that represents the mean of 29.881. So just by looking at it, we can kind of tell that it's a positively skewed distribution. We see more of a tail drifting off to the right, although the mean and median are somewhat close. The fact that the mean is to the right and the slight positive skew, which would suggest that we have more extreme values on our right. There may never be another Titanic, so let's consider this the population of Titanic passengers. And a question we might ask, are there groups distinct from each other in terms of age? One of the nice things about looking at distribution is that once we see it, we may naturally have a follow-up question on whether there are group differences. So now we're going to compare men and women. On the left, we have female passengers, and on the right, we have male passengers. And we have their distributions on their age. We have the vertical lines that represent the mean and the median. We have them for both distributions. And just like the main distribution, we have the mean, which is the orange line, slightly to the right of the median, which is the dashed purple line. The mean for women is 28.687 and the median is 27. For men, the average is 30.585 and the median is 28. So men are about 1 or 2 years older on average than women. So just by looking at these distributions, they sort of resemble the overall distribution. We see in both slides that we do have a higher frequency on the lowest ages. So We can guess that there are many infants and toddlers on board the Titanic, and we also have a positive skew as well. So just in terms of shape, the shapes look similar, although you'll notice that there is a higher frequency of male passengers. And it's important to note that for the staff and sailors on board the Titanic, the majority were men. So that could explain this higher frequency of male passengers. There were about 400 more male passengers than female passengers. So not only do we have a higher frequency, but we appear to have a tighter distribution for women on age. Their age range mainly goes from 0 to about 65, and there are probably very few female passengers between 65 and 75. The 75 to 80 group, there are some. Just maybe in this view, it's hard to see that. But we probably should feel comfortable in saying there might be more of a narrower distribution for women. But overall, they don't seem that far different. So what we'll want to do is analyze the data a little more. And in this slide, here's an analysis and an interpretation. So we'll first start on the top with our descriptive statistics and the description of it. When comparing the average ages between men and women, both distributions look alike and look similar with the overall distribution. The means and medians only differ by about 1 or 2 years, with men being older. Now I'm going to go to the second bullet, which has information on some of the inferential analyses I've done. We haven't covered this part yet, but we will in the next few weeks. But I'll just include this interpretation. First, we have a statistical test shows that the difference is slightly significant. There's a p-value of 0.04. You may have heard of p-values before. Just the lower the number is, the more rare or the more unlikely we are going to be wrong about saying something's different, that we have an important finding. It meets our criteria, but it doesn't appear substantial. If we're to go back, we can say, well, if anything, it just looks like there are more men, but in terms of age, it seems similar. So it meets our criteria, but it doesn't appear substantial. And that's an important thing to keep in mind, the difference between significant and substantial. One of the first questions you might get asked when you report your results is it significant? And the follow-up might, if the answer is yes, the follow-up might be, is it substantial? Does it mean a lot? Is it important? I examined statistical power, and it is weak. For example, if we repeated this experiment 100 times, we probably would only find a significant difference about half of the time. In other words, we shouldn't expect to see a lot of consistency in these findings. So a p-value of 0.04, it says there is some difference, but how consistent is that difference? Probably not. It's not at all consistent. And if it was a substantial finding, then we'd expect more consistency in those results. So what we can see is visually there looks like they look the same, but maybe there is a difference. But then when we got into our inferential statistics, then we can use our results to confirm or validate what our beliefs are. Okay, so now we'll consider age by passenger class. We looked at the difference between men and women and didn't see a lot. We saw something that could be important, but suppose you're working on something within the hospital and you're looking at maybe an intervention, or maybe we're looking at a difference, something that we might have different readmission rates that are different this month than compared to the previous month. They might look a little bit different, but we'd want to use these tools to point out to our clients or our department leaders and say, well, they might look a little bit different, but statistically they're not significantly different. But in this example, we'll consider passenger class to see if there are any differences there. And so from looking at this, we can start to see differences between our different groups, most notably between first class passengers, which we see in the top left, and our third class passengers, which we see on the bottom left. Actually, this bottom, the third class passengers probably look most similar to the overall average. And a big part of that may be because of the number of third class passengers. They're the biggest group. Our second class passengers begin to resemble more of that overall population, but we don't have that high frequency of 20 passengers in their 20s. But we do see a lot of passengers in their 20s in our third class passengers. And it's important to note that staff and sailors were made up a big part of this third class. And the majority of, or the biggest age groups were 20 to 30, 20, 25, and 30. Each of these bars represents 5 years. So if there are differences, we'd probably expect to see the biggest differences in age between first and third class passengers. The mean age for first class is 39.16. For second class, it's 29.507. And for third class passengers, the average age is 24. The means and medians are remarkably close. They're only off by about a year. And the age difference between first class and third class is 15 years. So now we'll analyze this data a little bit more. And in our analysis and interpretation, I compared the different passenger classes, and we can see that the distributions appear different. First class has a wider spread in ages, while third class clumps up around the younger ages. And in our inferential statistics, we see that a statistical test shows a significant difference, p equals 0.001, which means it's a very low chances of us being incorrect in this interpretation. We see a significant difference with the very high level of statistical power, about 100%. So if the Titanic didn't wreck and there were decades and decades of service, we'd expect within a similar time period that we would see those significantly different age differences over time. If the 15-year difference in average age seems important, then we can say that we have substantial findings. So again, we begin with our descriptive statistics, and we do that by looking at our distribution and describing the center and the spread. I didn't report the find number summary or standard deviation in this slide, but in a proper assessment, we would consider both the center, which we have here represented by the vertical bars, as well as a measure of variability such as the interquartile range or the standard deviation. And another thing to consider is the shape of that distribution. So when we talk about skewed distributions or flat distributions, the top left looks somewhat uniform, meaning there are equal values across the different ranges. It's not quite, but it's starting to take on more of a uniform distribution appearance. That gives us a lot of information about our findings. And we can include that in our descriptive analysis, our descriptive statistics, and we can also perform statistical tests and make inferences about these differences between passenger classes. So within these sets of analyses, we can begin to identify trends and differences between groups, and we'll do that here with specifically for Titanic survival. So if we were to have an outcome of whether passengers survived or not, we can begin to look at mean rates between groups, such as men and women or passenger class, but we can also look at trends in continuous variables such as age. And so we can begin to explain more about what is going on in the data. And we'll start at the top for age. This is an option that I have in my Shiny app. That's where this comes out of. And what it does is it breaks up continuous variables into quartiles. So each range that you're looking at represents 25% of the sample. So at the bottom quartile, the age is less than a year to about 22 years. And then the next quartile is 22 to 28 years. So this is probably your biggest group. Probably represents, the majority of it probably represents the crew. And then our third quartile would range from 28 years to 40 years. And our biggest quartile, which has a broader range, which is reflected by that tail in our positively skewed data, that age range will go from 40 to 80 years. And so what we can see here is that there's somewhat of a linear trend. And by a linear trend, that would be indicated by as each quartile changes, we would see a pattern emerge. So in our oldest passengers, that mean is down here almost to the far left of the four groups, but not quite. And then the rate of survival increases as we move up to the next line that represents younger passengers. We don't quite see that happen with our passengers in their 20s. Actually, they have the lowest rate. If it was perfectly linear, in the sense that the survival rate increases as we go from one age group to the other, we would expect to see it here. But since a big proportion of this age group are crew members, we see that unfortunately as our lowest group. And then our youngest passengers have the highest rate of survival. So this is more of a nonlinear trend, but we can see somewhat of a pattern. And then we go down to the sex variable to see the differences between men and women. We see big differences in distributions between men and women. On the x-axis, it shows the rate of survival, and we see that goes from about 0.2 to about 0.7. So for men, the survival rate's less than 20%. For women, it's close to about 75%. So you can just see the spread in group center values, or in the mean values. We don't have the distribution here to look at, but you can just see how big that difference is. So this would tell us that this is probably an important factor in how passengers survived. Just a big difference between men and women. When we look at passenger class, which is towards the bottom, it's P class, that's passenger class. This is more of the linear trend that I spoke of earlier. We see for the third class, the rate of survivals over here on the lower end, maybe about 25%. For the second class, it's probably about 42%. And then for the first class, it's probably closer to about 63%. So we see that pattern of the survival rate increasing as we go in reverse order from the third class to the first class. So there's a pattern there. So this may be important also for understanding survival. And this looks pretty consistent, and we also see big differences between the first and third class. And overall, the survival rate was about 38 to 39%. And we can use this value as well. This is the overall survival rate. So red dots above the overall dot might have above average chances. So if we look at passenger class, we can say, well, the second class might have had a better chance. We're not sure how far what this range is. We're just looking at the center. We don't know if a likely range of values might cross over into this overall level. But we'd probably feel pretty confident in saying that first class passengers have a much better rate of survival. So going back to the what we can do with statistics in terms of telling a story, I think for the Titanic data, it's a good example of women and children first. I think if that's a story that we can tell, I think that would be accurate. And also passenger class, first class passengers seem to fare well. In this slide, this comes from a regression I did, and it's a variable importance plot, so it indicates which factors contributed the most to understanding survival. And it also confirms our descriptive analysis on Titanic data. So all three of these are significant and important variables. But if you were to rank which one had the biggest impact, it was probably the sex variable. That was a pretty good indicator of a passenger's survival, and we see that this red circle on the right gives us an idea of how much more important it was than the other predictors. It's important to note that these were all very important predictors, but some more so than the other. Age, of the three, it was the least important, but still it's an important predictor. And passenger class was also important. So we can begin with our descriptive statistics that can move us towards our inferential statistics, and really they work together to first put you in the right spot to analyze data, but also it begins to open up, gives us opportunities to spot differences if we're just looking at a distribution like this, then that can give us an idea of what might lie ahead. Understanding that when we look at values, we're not just looking at the means. They could look similar and not be that important, or they could look similar and be we might have some significant differences there. But we also want to, so when we analyze data, we want to look at the center. That's our mean or median or mode. We also want to look at the spread or the variability, and that's either the standard deviation or the interquartile range, or just our percentiles. And we also want to take into account the shape of the distribution. If things look very different, then we can test to see how different they are. And I have in the appendix, I have different examples of skewness and kurtosis. This is a normal distribution with a slight left tail. Another way to describe that is it's mesokurtic with a slight negative skew. We can tell it has a negative skew because the tail drifts off to the left, which pulls the mean to the left of the median, but the mean and median are still relatively close. In this slide, we have a right tail or positive skew. The right tail is another description of a positive skew. The tail drifts off to the right, which pulls the mean towards the high values and to the right of the median. And here's how far our right tail goes. And in this slide, we see a widespread distribution and heavier tails. We can describe this as Platykurtic, almost a uniform distribution. This uniform distribution part, we see that because for each of these bins, they're about the same level. A perfectly uniform distribution would almost look like a square or a rectangle. This is somewhat close. It's important to note if we were to change the number of bins, the number of bars that we have in this histogram, we might see more of a normal distribution if we were to increase the number of bins. We see that the mean is to the left of the median and suggests a minor left tail. So our mean is 11.52 and our median is 12. So it's just a slight left tail. With the standard deviation of 5.37 and a coefficient of variation of 0.47, we may think of it as a slight normal distribution. We may want to adjust our histogram settings. Again, this comes out of my Shiny app if you wanted to take a look. But so the shape of the distribution may not be accurate, and that's an important part about statistics, is that we use our distributions and our statistics, our summary statistics together, because by looking at just basing it off the distribution, we may miss, or we might miss something, but we may also misinterpret something. And then by only looking at our summary statistics, we might have two very different looking distributions, but according to the numbers, they may seem similar. In this slide, we have a narrow distribution with the right tail. It's leptokurtic and has a positive skew. So we can see, you can barely see that the tail comes out, but it's coming out at least past the value of 15,000. I think if it's being printed in this graph, it's probably closer to 20 to 25,000. I just can't see it in this graph. Graphing is helpful for understanding the distribution, but we need to be careful not to overlook important statistical properties. This variable has the highest coefficient of variation, even though it appears to have the least variation. It looks like a narrow distribution here. The reason is how the standard deviation is calculated, and because highly skewed data inflates the standard deviation. So we have a very narrow set of values here, but we also have extreme values on the right. So when we actually do the calculation for standard deviation, that's kind of one of the worst case scenarios because it really inflates the standard deviation. Although the distribution is skewed, you can still make use of the mean. For example, cost projections. It is the estimation of the standard deviation that is most impacted by skewed data. So that's the course session. We'll have week 2 soon.